Okay, guys. Yep, it's past 9:10, so let's start. I want to start today by reviewing and addressing something from last week. Was that we talked about the nonlinear problem, finally with the XOR problem with using perceptron to solve the XOR problem. I had drawn a graph that had to do, or a plot that kind of illustrating why the single layer perceptron cannot be used to solve an XOR or a nonlinear problem. And it was a little bit confusing. It's supposed to be 3D, but I think because of the way it was drawn, it didn't appear like, oh, you know, why can't the single layer perceptron solve a nonlinear problem? And let me refresh everyone's memory. So we had a case where if I were to plot, so remember, our single layer perceptron works like that. So if we have AI1 here, and AI2 here, and AJ here, and then, you know, this is like the basic setup here. And the idea here is that if I had a problem, which is the AND gate, and I have AI1, AI2, and well, don't do the AND here, but let me set it up so that if I have AJ, and this is an AND problem, right? Then it will look like this. 0, 1, 0, 0, and 1, 1. If it's an AND problem, this is the output. If it is an OR problem, then it'll be 0, 1, 1, 1. But if I go to an XOR, I have a case where I'm going to put this in the middle a little bit so that it makes better sense. Okay? If it's an XOR, then it becomes something like that, right? Okay? So this should be easy, nothing new here. Then I have drawn the plot, the problem here. I'm going to shift it a little bit. Excuse me. Such that if I have AI1 here, and if I have AI2 here, and if I had a third dimension, okay, which I'm not going to draw yet, okay, then, you know, somehow how the different states of AI1. So if this is, I'm going to keep this as 0. So if 0 is here, and this is 1 on the AI1 axis, and this 0 is here, and 1 is here on the AI2 axis, somehow because of the AND problem, if I have 4 possible outcomes on a third axis, right? That wouldn't have you wouldn't be able to separate the two binary outcomes of the third axis. Okay, the fact is that actually if you have a single layer perceptron, there's no third axis, right? There's only 2 dimensions because you only have one AI1 input and an AI2 input. So you only have these 2 axes that you can play with, all right? And the third so-called situation, it's not an axis, okay? It's about the state of that coordinate position. So for example, if AI1, the way to think about it is like this. If AI, in an AND logic gate problem, if AI1 and AI2 are both 0, then that location is, let's just say that there's a red dot. It's a red state. It's a red situation, okay? But if it is 0, 1, 0 for AI2 and 1 for AI1, it's also red. So let's put this as red, and then this situation is also red, okay? But when it comes to when both are 1, okay, then it's a yellow state, all right? So in other words, when you have the state for when you have the inputs are both 0, so let's say those are like cat features, okay? is that this is what makes it a cat. But if you have only one other feature that's on, okay, it's still a cat. Or the other feature is on, okay, it's still a cat. But if both features are on, then it becomes a dog or something like that, okay? All right, now in this situation, you can linearly separate the yellow from the red dot, right? So no problem there, okay? And if it's an OR, it becomes an OR, then it is like this. Oops. It's just one red color at when both cases are 0. But then when either case at least is a 1, right? Then they become yellow. And you can see clearly that all I have to do in this case is to shift my criteria boundary just a bit lower, and I can still separate with one straight line the yellow dots from the red dots. Okay? So in both these cases, these are linearly separable. Okay? So the AND and the OR problem are linear problems. They are linear. Their solutions can be linearly separated. All right? In the case of a single layer perceptron. Now, when we have an XOR problem, okay, it looks like this, right? So in the XOR case, the red is here, the red is here. So what will be? Red is for 0, 0, and 1, 1. So it'd be like this. Okay? And then the other two cases are yellow dots. All right? Now, when it looks like that, on a 2D plane, there's just no way to draw a straight line, right, to separate the yellow from the red dots. I mean, you can draw kind of like an ellipse like this, but it's not a straight line, right? Okay, so how do you solve this problem? You can't solve it with a single layer perceptron. You need a multi-layer perceptron, MLP, multi-layer perceptron. And in last week, I suggested this diagram or this graph or this architecture, right? Correct? And then so you have the AI input units, the AH hidden units, and then the AJ output units. Okay? So now in that case, what that means is actually, so yeah, this was the error here, was that you have hidden unit IH, IJ, and then H. Yeah. Okay? I guess you could have it. In this case, I drew this solution for you. Actually, if I just wanted to add one more dimension, this will work as well. Okay, so this is AI1, AI2. This one is AH, and there's only one of it. And then there's AJ. Okay? This is an alternative network, a multi-layer perceptron that will also work for the XOR problem. Okay? And so effectively what this will do is to add one more dimension at the third dimension here. And you can see that if I do that, then, so that also I was trying to draw, is that so if this is 1 here, okay? So then the yellow dot comes out of the plane, okay? And then similarly, if I draw it here, then the yellow dot comes out of the plane. Let me erase those two previous ones. All right, and for those of you who can visualize it pretty well, you can see, therefore, now I can, because this is outside, right? This is outside, but the red dots are in the plane and the yellow dots are coming out. Then what I can do is I can draw sort of like a plane that cuts the yellow from the red dots, right? And all I needed was this extra AH dimension to do that. And therefore, you can then, in that case, separate the XOR problem. Okay? This is just a minor clarification to update from last week, just to make it clear why, when it is a single layer perceptron, it cannot solve XOR. But then what does it mean that to add a third dimension in terms of the states of the positions, and therefore why a multi-layer perceptron can solve the XOR problem. Okay? All right. So, but that being said, okay, last week I suggested this to you guys, right? And then I think, I don't have people been looking at the homework 2 yet? Not yet? Have you? Okay, homework 2 will maybe get you to try different things, but this is another architecture, okay, that will be able to do the nonlinear problem. You can go and try and explore. I gave you the tools last week from the Google Colab, right? You have the Jupyter notebook so that you can copy, paste, or edit, or whatever, and try to integrate that with your homework too, okay? Really, the way to learn from this course is to get your hands dirty, go try it out. And you know, traditionally, we figured it out on our own, and then we had to kind of like do our code from there. It was very painful, okay? So now that we have AI, I figured I just give you the Google Colab, you know, and then you can use it from there, and you can work with your AI together collaboratively. And then, but the real challenge is to solve real problems. And so this is, in homework 2, we give you some challenges for you to test your knowledge about perceptrons, okay? All right, at this point, any questions about perceptrons and for last week's lecture to just this lecture? Because after this, we're gonna move on with the Hopfield network. Any questions? No? All good? Okay. I have one more thing to talk about, and then we'll go on to the Hopfield network. So with this architecture, remember, so this was the architecture. For the single layer perceptron, we talked about architecture. We also talked about the activation function. Okay, and the activation function was such that Aj is equals to 1 if, right? It's 1 if the sum of the weighted inputs is greater than theta, or otherwise it's 0, okay? That is the binary ReLU. Okay, and it looks like this, right? This is theta, this is the matrix, the matrix operation of the input, and this is the output. So it looks like that, okay? And it would be the case that if you are talking about AH, these units here, okay, it would be considered AJ relative to AI, right? Okay, so remember, it's always I to J, or H to J, or I to H. Okay, so it's just relative transition. That's how we talk about the activation function. All right, we just put the indices there so we know that what comes first and then what comes after. But it could be H, it could be J, it could be K or whatever, depending on how complicated your network is. Okay. All right, so this was the activation function. And I want to bring this up because I do want to mention also, and I hope you've read it in the, I hope you've read it in the Agarwal chapter. So give me a second while I pull this up. I want to also convey to you this way of examining or of understanding the activation function and how it is to do with the sums of the weighted inputs and then applying a nonlinear transformation. This is important before we move to the Hopfield because you'll see, you have to break things up a little bit more specifically, all right? So in Agarwal has a nice figure, and I think we should all know it pretty well, perceptron. In Agarwal, he draws this picture of the perceptron that you can think of a perceptron as having two parts. We have a summation part, okay? Because, you know, I write it like that, right? Like the AJ, the output, is a function of the weights of the input, okay? The weights of the sum of the weighted products. And in Agarwal, it's visualized like this. We first have, before we get to AJ, we have AJ star, okay? And AJ star is the pre-activation state, okay? Pre-activation state, okay? And the pre-activation state has a pre-activation function, and the function okay, in this case, it is a summation. It can be anything, it can be a product, it can be whatever, but in the basic neural networks, we usually just use summation. Summation of what? Well, summation of the weighted inputs. Okay? So this will be, if I have 4 units, and this would be AI1, and so this also get used to the notation that we will use. I can have k input units. It doesn't have to be just 2, it doesn't have to be 3, it can be k, many, 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 okay? And in which case, correspondingly, each of them will have the weights and the notation should be like this, okay? That feed into the pre-activation state, and what it does is basically WI1J times AI1 plus WI2J times AI2 plus so on and so forth until WIKJ times AIK. Sum all of that, you get the pre-activation state, okay? And then from there, this will be the activation state, or we call it the output state. Okay, the output, the final output. And you will note that, therefore, this is the activation function. F, this thing here, okay? And you can see that the graphic is it's a nonlinear, it's the binary ReLU, right? Okay? So in one case it's the summation, and then the other case is the binary ReLU, all right? And then this gives you the final output, or that where in this case AJ is equals to AO. Okay? All right, so just to get you used to this, some notations to emphasize again. Notation, ith layer is the input layer. Okay? And then we say something like the jth layer correspondingly is the output layer. And then we have the kth unit. Okay? All right, so it's layers and then units, and then like layers feed into the next layer and things like that. That's the notation that we're going to use, all right? And so if you draw it out graphically like that, I hope that when I write something like this, it's very clear what it means. Okay, that is just the mathematical way of expressing this figure. Okay? Or similarly, that the function is the sum, right, over I of, correct? Okay? Because this is just the matrix form, right? The big W and the A vector, AI vector, which is equivalent to the summing of the products, right? Which, effectively, if we go back to that this is the binary ReLU, okay? And if you remember, the binary ReLU is, and if you remember the Google Colab that I gave you, is actually max of the sine of the WA I minus theta 0. That's the function, right? That's the actual implementation. So this is equals to I minus theta 0, like this. Okay, so the function is that max sine composite, okay? And that is the activation function, which takes the pre-activation state, which itself is a pre-activation function, which is, in this case, a summation. So you've got to think of things like that. It's like a function within a function, and then it is operating from one layer, across all the units from one layer onto each unit across the next layer, the subsequent layer, okay? And oh, by the way, another terminology you will come across is we think of this as upstream, and this is downstream. Okay, so I'm laying all these terminologies and concepts here first, because when we go later on, you will come across it again. Okay, so now, so if you are okay with this idea, or this representation, then in Agarwal also, just to mention, we've always talked about the binary ReLU. So you are familiar with this one, where the output is equals to the max sine, oh, well, yeah. Let me do it this way first. Other types of I might have mentioned this briefly at the beginning of the course, but it is not that we only have the binary ReLU, okay? So like it's not that the binary ReLU is, so if I were to use AO instead of AJ, but it's the same thing, right? So the binary ReLU is max of the sine of, I'm going to tell them in a bit. Give me a second. Yeah. Okay, so this is our binary ReLU, and it looks like this. This one is here. This is theta, and this is 0. This is 1. Okay. We also have, very simple, sine. We actually don't need the max. Okay, think about it. Okay. Yeah. Just directly the sine of this. Yeah. Okay. Actually, then you don't need a theta. Okay. Because if it's the sine, then it also looks like this. So it's 1, but then it's minus 1. This is 0. Okay? And theta is 0. Okay? You can do that. You can have another kind of activation function is that if I were to draw this, if I were to state it like this, what is the activation function? It's just 1. Right? Which means, what does it look like? What does it look like? It's a straight line. Right? Okay? It's a legitimate activation function. It's just not a nonlinear one. Okay? Okay, then there are others. So we have this one, and you have, this one is quite famous. Okay, and this is sigmoid. All right. We have so many. Okay. Okay, which is equals to yeah. If you work it out, it equals actually the 10. Okay, what does this look like? It looks very complicated. But what it is the sigmoid, but just shifted. Okay. You can also have and this is the classic ReLU. Okay, so here we have the binary ReLU, binary regularized linear unit, and here we have the regularized linear unit. All right, and then finally we have max of the min of A star one minus 1. Do you know what this will look like? So if it is the so this is the binary ReLU, is this one, okay? So if it is the sign, if the max of the sign of that difference and the max of the min, it turns out that the max of the min, oops, looks like this. If you can imagine, there will be some range. This is 1, and this is 1. And there will be some range where there is some slope, right? But then there is a maximum as an asymptote. And we call this the hard tanh h. Okay, because this one, the tanh h, tangent, is kind of keeping the activity. It can be negative, it can be suppressed, it can be positive, but they have a limit. They don't go beyond 1 or minus 1. In the case of the hard tanh h, it's regularized, it's flat, right? So it's kind of like, in one case, we have a more continuous function, like the sigmoids, okay? So that we allow for some smoothness in the transitions, right? Or alternative, but you know, that adds some complication. It might be more biologically correct, okay? but and it actually allows us some very nice derivatives. We will see that when we do backprop. But it's a more complex thing, right? This is easier, right? Much simpler to understand. It's a hard edge, and then it's like very clean, okay? So this is good or easy to do in computers because it's like very digital, right? This one is on, this part is off, this part is on by how much, and all that. It's very fixed. This part's like where it's more continuous, it's more biological, okay? And when it comes to computing, it leads to some issues because you will get things like 0.00 whatever floats, okay? Which when it comes to computation, takes up more space than integers. Okay, all right? So this has nothing to do with the modeling or what's real or whatever. This is just practical when you want to implement in a computer system. You have these things to think about. So we, of course, want to try to model things as close as possible to nature, and in which case you would assume that it should have a more smooth function, okay? But then sometimes it might be just detail, and we don't care so much about that detail. We might want to use something that's just more practical for a computer, okay? Computer, however, has a problem in that if we were to do the derivative of this, okay? And I'm going to introduce some math here. Oops. No. If I were to do the derivatives, how many of you all did calculus, right? 微积分有没有？有吗？ Do you remember at all? Okay, the derivative, when I have this expression, means how does AO change with respect to A star J? So if A star J change a little bit, how much does AO change? So it's a slope, actually. It's just a change. And the thing is, if your function for AO originally was this function, right, this relationship, then what is the change in AO per AJ star? Well, when it is less than theta, the change is 0. AO doesn't change no matter how AJ star changes, right? And when AJ star is greater than theta, then the change is also 0, right? So the derivative is 0, be lower than theta, and 0 when higher than theta. But here's a very weird thing. What happens when it is exactly at theta? The derivative is infinite. So if you think about it, mathematically, 这个不漂亮, okay? Like, oh, how come it's 0, then infinite, then 0? It's like, what is that, right? I mean, it's nothing to do with it. It's just, that's just the way it is, okay? But you can imagine here, see, because this is like to infinity this way, and to negative infinity this way, right? But there's a maximum here is like 0 and 1 here, okay? So it never reaches 0, it never reaches 1, and in between there's smooth. So that the derivatives 是漂亮的. There's a gradual from very low number to high number, and then go back to a low number. So it looks actually very much like Gaussian, almost. Approaches Gaussian. Okay, and obviously you all know statistics, you know how powerful the Gaussian functions or how practical and useful they are. Okay? All right? So I'm just highlighting this, a bit of math here today, okay? So that actually later on there'll be quite a lot of math, but it'll be something like that. That you have other types of activation functions that Agarwal mentions, and you will see that in papers, in publications, and you might be wondering, oh, why engineering papers always use ReLU, and then why here we might be talking about binary ReLU, and then some later on in backprop we will be using the sigmoid function and all that. It's like, what's the difference between these, apart from the architecture, like you have a single layer perceptron, multi-layer perceptron, and then you have So apart from that, having these kind of different architectures, we also have different activation functions. Why must we have different activation functions? Well, because, well, first of all, obviously, our neurons might be activating in different ways, right? But beyond that also, there's this notion that when you are trying to model nature, you might want to have a smoother function, so like sigmoidal. But it might be more practical to use just a hard function because computationally it is easier to handle. But they all come with pros and cons. If you handle things in binary or hard computational sense, you lose the finesse, some maybe applications that might come when you try to take the derivative, okay? But if you theoretically think of things sigmoidally or smoothly, the derivatives gives you some nice tools or some nice solutions. This will really come into play when we do backprop, because backprop totally relies on the derivative to justify, to prove that backprop works as gradient descent. This terminology will come in more clearly later on, okay? But at this point, I just want to highlight this to you, okay? And so you might get the feeling, okay, we're getting deeper and deeper into some theoretical and mathematical grounds, and it will become worse, okay? So, but you'll get used to it. Don't be afraid, all right? Because we want to break this down and to understand the concepts. You don't have to worry about the technical mathematical things, but just be aware when you know, I hope that if you see these things that they sort of make conceptual sense to you, so that when you read it or when you deal with it, it's not so scary. You know, you don't have to know the specific math, but as long as it makes sense to you at some conceptual level, I think that's already pretty good, okay? To be clear, it might take you, it's not like you can get all of this like in one reading or in one sitting. You're gonna have to read it over and over again and maybe deal with it, you know, for a few months or years before things make more and more sense. And they will make more and more sense as you go along. Okay, so I think that's what I want to deal with respect to the perceptron, and I want to close this chapter right now. Any final questions about perceptron? Yeah. Mm-hmm. Yes. Yes. Did I get it wrong? Oh, yeah. You mean here? Yeah. Yes. Yeah. It's because it's usually constant and all that. You can take it out, right? Yeah. So you can put it there. I believe. Let me see. Is that what Agarwal put? Yeah, that's correct. Oh, also that's just to let you guys know, you all can plug all these functions into the Colab, right? You can tell AI, hey, can you plot this? You can type this function, right? And then you can, hey, can you plot it out? And Google and Colab will like show you what it looks like. And then you can change, you can tell it, can I change some parameters? So the full function would be something like this. I believe, because here we take shortcuts. So there'll be a minus A star plus B, okay? Actually, this is the bias, okay? So that will come in later on. So like you can shift it up, down, you can stretch it, and then you can do many funky things with it, all right? And depending on how you change these values, then you can make the shape different. So for example, like if you say, oh, it's -1, you can just make A is -1. So -1 times -1 becomes 1. It's a legitimate mathematical trick or whatever, all right? Okay, anything else? All good? All right, so then I'm going to close this chapter on the perceptron, and we're going to talk about the Hopfield network. Okay, and for that, so for today, we won't be needing our computers. We will be really just talking theory for the whole deal. I'm just going to introduce the problem at hand, and then we'll take a break, and then we'll talk more about it. But first, let me just highlight, okay? So the Hopfield network Oh, wait. Okay, so administratively, I forgot to highlight this. So homework 1 is due tonight, okay? I hope everyone has handed up, or if not, you can hand up. Homework 1 is so easy. Just hand it up, and then you're done. Homework 2 will be due next week. Homework 2 is a little bit more challenging. You will use the tools we highlighted, okay? But it should be okay. If you have problems in between with homework 2, feel free to email me, and we can, I'm happy to guide you. So we are going deeper and deeper, and now this is the first. So Hopfield we will be releasing the assignment for Hopfield network, right? But Hopfield is one of the key we have 3 networks that we really want to deal with in this class. This is the first one, and I need to highlight to you, this is the Nobel Prize winning work. Okay, so if you can do this, you can get Nobel Prize. No. Because John Hopfield's Nobel Prize is for this work. I mean, obviously people have done it before, so if you do something that people have done before, no one will give you a Nobel Prize, right? But I just want to highlight is because I've given you the paper, right? You have the John Hopfield paper, right? Read it. That's Nobel Prize winning work. Try to understand it. I think it's very inspiring. So if you read it and you understand it, or you struggle with it, okay? I can't say that I understand every single thing. I'm pretty sure I missed some things because it's such a rich piece of work. But every time you read it, you gain something, right? And you'll see how these scientists work. It's the way they think, okay? All right? And I hope at a personal level, at least, as an academic, that you are inspired by this paper. It's not an easy paper, okay? I'm not saying that he writes very well, but I'm saying that if you spend time reading, you can get into his thought process, okay? All right, so Hopfield network, the Nobel Prize winning work, is also known as, or you can also think of it as what it is doing is making, or the network itself is an autoencoder. And by autoencoder, we literally mean that it tries to encode auto itself. Auto is the name for the word auto means self, okay? And also, it's an attractor, okay? Because you will find that it attracts states to some attractor states. And we will understand that more later. I'm going to add one more. What it does is a kind of principal component analysis. PCA. You have done statistics, multivariate statistics. You will know what is PCA. Actually, the Hopfield network is a kind of PCA. And if you know PCA, you will know that it is a singular vector decomposition. SVD, okay? That when you do PCA, you are also doing SVD, or rather, that to do PCA, you actually do SVD. If you do not know what PCA and SVD are, don't worry about it, okay? It's not important, but I'm just, in case in the future you ever come across these terms, I hope you can make the connection. You might suddenly, oh yeah, suddenly it makes sense. But we will deal with it from the Hopfield network perspective. These are the same thing because they're so fundamental. That's why these are Nobel Prize winning works, because they're so fundamental. You will see their appearance across many different fields, maybe in different forms, but then you realize, hey, it's all the same thing, and that's why this is so important, so fundamental, okay? All right, so in Hopfield network, Yeah, so I have a few minutes. We'll introduce this and then we can take a break. This is a good timing. As with any, as we stated, we're going to use the framework that I introduced when dealing with neural networks in class. What's our goal? What's our purpose that we are trying to do? We're trying to model something in real life in our biological neural networks, and in a sense of how these neural networks, our biological neural networks, carry out or conduct a behavioral phenomena, okay? The behavioral phenomena that Hopfield wanted to address is a big one. Memory. Okay? We all take this for granted, really. Okay? I mean, sit down and think about it. You are your memories, isn't it? If you have no memory, so let's say you have Alzheimer's disease. Even Alzheimer's disease is not a perfect example because you have already made some memories in your life, and then when you have Alzheimer's disease, you cannot make new memories, essentially, okay? But you still have your old memories, so you are still you, okay? Imagine an organism or a state of living where there's just no memory whatsoever at all. From the moment you are born to the moment you die, you don't remember anything. Are you even you? Are you even alive? Right? So you see, this notion of memory, okay, if you think about it, it's actually very philosophical also, okay? All right, so I'm going to ask, what do you all think memory is? We would like to do this exercise, and then we can see what different definitions people have, okay? So let's start with William. What do you think memory is? How do you define memory? Yeah. Yeah. Don't need to think too hard. Just whatever comes out of the top of your head.
All the information we sense, and it got saved into our brains.
Okay. That's pretty decent. Yeah. Okay. Okay. So you.
Actually, it's something you remember, you can retrieve.
You can retrieve it. Something that you remember and you can retrieve it. Okay. How about Ben? Okay, you can store. So let's write this down. Okay. So you said you can. What do you say? Remember information. Yeah, that's saved, right? Info that's saved. And then you say this info can also be retrieved. And then you said stored. Okay, all right. Explicit. Okay, so. You don't know what? Sorry? How you can do some actions? Okay? Right. Almost the same thing? Nothing new to add? Okay. And decentralized. Okay. That's our memory you're talking about, right? Okay. All right. This is our very classic, okay, and all correct. Nothing wrong there. It's all pretty accurate. That's you describing your memory, right? Our memory, right? Can I ask you, when you talk about When you buy a computer, the 老板 asks you what memory you want. Is use also memory. What is that talking about? Also memory, right? Is it different? We feel it's very different, but we use the same word, memory. Can someone tell me when you say the computer's memory and then all this memory that you are describing our experience of memory, do you think you're talking about the same thing? Or do you talking about different things, completely different things, or like where is the commonality? Are they exactly the same? No. Are they completely different? Ben says completely different. You think completely different? No, you don't think it's completely different. Okay, Ben, why do you think it's completely different? Oh. Emotions and what? Experience. Okay. All right, this is interesting. So you're saying that our memory and the computer's memory is different because of the emotion and experience aspect. Okay. So, and that's they're completely different? Okay. You don't agree?
Yeah.
Okay, why?
There's something common.
Some common.
We save information, just like hard drive, and we also retrieve memories, like computers,
Do we do it the same way?
but in total different way. Yeah.
Okay. Okay, so the functions are the same. Or at least some functions are some results of the functions are the same. So we can say that we save and we retrieve, we store and we retrieve. So that's the same definition. To store means you get some info, you put it in this thing, and to retrieve means you take some info that was in there, you take it out, right? So we do that. We have this experience of doing that. But in a computer, you also can say that of a computer. You put some information into these logic gates, right, into the disk itself, the flip-flop gates, and then you can read it and take it out also, right? So there is some commonality there, okay, in terms of at least in some operations and functions. But then there's very clearly some distinction. You're talking about something, and I highlight this is very important, okay, the notion of experience, because does the hard disk experience anything? You think so? What is experience? What does it mean to experience something? Why do you say the hard disk doesn't have experience, but you say you have experience? What's the difference? Okay, let me put it in another way also, okay? If I have this thing here, right, and I punch it, okay, did it experience anything? No? You think so? You don't think so? Okay, but if I punch you, you say you experience something. Okay. Why? What really is the difference here? Okay, let's think of it this way, okay? You are a bunch of molecules and atoms, isn't it? I mean, if you can say your neurons are doing something fancy, sure, but your neurons are made of molecules, atoms, and all that, right? Okay, what's really happening at the level of the neuron is these atoms and molecules are receiving some signals or energy, and then they are changing their states, right? Correct? And somehow some complex interaction there, we say it's experience. We have experience because something happened, some information that has been influencing our molecules and atoms of our neurons, and then as a whole collective, we feel something, we experience something. Is that okay? Is that acceptable? Okay. This is also made of atoms and molecules, isn't it? It is also, I just hit it. It's my energy, some information. I made it to, did it change its state? It did, right? Because, I mean, it bounced back, but for that moment, it changed its state. If today I have a, okay, so I have a napkin, right? I fold it. I impose some energy on it. It's changed its state, right? And it's also atoms and molecules. Why this one doesn't have experience? And then for us, we're so selfish, we think we have experience. only we have experience. Okay, there's no answer here. It's very philosophical, right? But you have, I'm trying to get you to think about it because this is, again, Nobel Prize winning word, right? It's a very fundamental question. When you say, we always talk, I said, we always take this for granted. We hardly think about it, okay? But the fact is, actually we don't really know at every second when we say memory, what we mean by memory. I think we can get there, but we have to really sit down and think, what do we really mean? When I probe you, you come up with all these concepts and notions, which are very legitimate, okay? But let's challenge ourselves what we really mean, because I would suggest to you, this is memory, okay? And it has experience. The thing has experienced some energy on it. So if we talk about it, if for me at least, you might have a different opinion, at least for me, I think experience just means that you have some energy going into this object, okay, or well, let me draw it this way. And then change of state. So if I have energy, this energy came in contact with this object being made of a set of molecules and atoms that define this object, as opposed to another set of objects that didn't experience that energy, okay, relatively speaking, okay. Then that object had a change of state. For me, I think that's memory, okay. I don't know if you would agree, but why do I say that? This because why this, I said this has memory. My definition of memory is that I have an energy that induced some change in the state of the physical state of this object, and you have no problem thinking about it that way because it remained like this. It didn't flip back, right? It remained like that, and then I said it has energy. So just like a computer logic gate, you turn on the electronics, it caused the flip-flop gates to, some gates are on, some gates are off, and they remain that way. This is a physical thing, isn't it, right? A semiconductor is really physically the electrons in some state or another, and it remained that way. So it has memory. It took some information from the electrical energy that we type or we change certain things, and we made the gates change their state, and they remain that way, thankfully, for a long, long, long time, right? It didn't get erased, okay? However, some other types of molecules and atoms, some other materials, don't do that. You put the energy in, it changed it for a moment, but when you removed it, or after a while, it lost that energy influence. So so we can think of things as we have energy which has information in it, influencing changes of states of objects, but these changes can either be permanent, forever, or relatively impermanent, very, very brief, okay? And really the only thing here is, i.e., time. How long does your state remain changed? Or does it like get perturbed or like go back, okay? For those materials, those kinds of atoms and molecules in which the states of change are more or less permanent, we say, oh, there's memory. So like a computer's memory can last much longer than our memory because there are states of change. Unless you do something else to it, it's going to stay that way. Okay? It's pretty much permanent. By that argument, a rock or a mountain's change, right? Because let's say 台风来, right? And then cause the mountain to have 土石流, right? Change the shape. It's pretty permanent. It'll stay there for years and years unless another typhoon comes and then changes it, right? I argue to you that there's memory there, right? You look at the mountain, I think Chinese people, we are very good at seeing this kind of allegory, this story. 是那个山有故事可以讲, right? Because we see it and we can appreciate that tells us what has happened in the past in this area. It's memory, just not our psychological experience of it. So this is very fundamental and profound, okay? So a rock that you hit has a pretty permanent memory. Water, if you hit water, 水, in your soul, you punch the water, okay? And you remove your hand, nothing, you can't tell that anything happened to it, right? Not like ice. You punch the ice, it will break. You can tell something happened to it, so you think that has memory. But water, if you punch the water and you remove it, it went back to the shape. But does that mean that it has no memory at all? Right? So it's just a time scale, right? For the moment that you punch your hand in the water, the molecules had to move, isn't it? Otherwise your hand cannot go through, right? So when you punch the water or put your hand in the water, the molecules had to move, but then when you remove, it moved back very quickly. So in other words, very short time. Not zero time. It had some very, very brief so-called memory, in the sense of memory, if we define it as energy that changes your status quo state. It had memory, it's just that that memory was very, very, very short in time. As opposed to some other materials where it had memory, you changed it by energy input, and it stayed that way. So it has very, very long time scale. Our memory might be in a range where we have sort of moderate time scale, right? You remember things in the order of days, years, months within your lifespan. As a species, we might remember things in our history, okay? But we also forget, we die, and then our states are lost. So it's kind of so artistic, right? Just like 比较长期, a bit more permanent, but not so permanent. So kind of like just a temporary function in time, so to speak. Okay? All right. So making your brains twist in knots here, right? But that's the idea here, is why this is so profound, and what question Hopfield was trying to get at had something to do with this. That we realize that our species has this notion of memory, but we never really challenged it. We never really defined it for ourselves what that really means. For Hopfield, he tried to answer this question by looking at the difference between different types of memory, okay? And there's two classes. All this that I just said might be summarized in two types of memory. One, which is indexed memory, okay? And then versus, which is what Hopfield is trying to implement, and is suggesting that this is what we do, really. Content addressable memory, CAM. Okay. We'll talk more about this distinction after we take the break. But so combine all the thoughts that have been trying to convey to you guys about what our memory really is, and all of what you just said is in the domain of content addressable, meaning that if you accept that our definition of memory being the energy changing your state, and therefore there's memory. That is a content addressable phenomena. Okay? However, computers, although I said that there is this change of state in the memory, but when we use computers, we are not using it for its content addressableness, so to speak. We are actually using it in an indexed way. Okay? And we'll talk more about that later as a distinction, because this is the problem that Hopfield was trying to distinguish back at the time, was trying to realize that, wait, the way we have made our computers and we say we have memory seems to be different from the way we talk about biological memory. Okay? That was the challenge or the problem at the time. Okay, so let's take a 10-minute break, and then we'll come back and we'll talk more of this exciting theory. So it's 10:20 on this one. Let's come back at 10:30. 10-minute breaks, okay? All right. All right, we're going to continue with the theory today. Okay, let's carry on. Hopfield network, and the goal is to deal with this phenomena of memory, which we take for granted, and it's not such an easy question at all. All right. So specifically, Hopfield was trying to mimic the fact that when we experience, as we say, talk about experience memory, we seem to feel like, or we all agree, have a consensus that our memory seems to have more of a content addressable kind of form or operation. We'll unpack that a little bit more later, as opposed to an alternative form of memory. Again, we will unpack that more later, but we call it index memory. All right? But these all should be understood in the big umbrella of the notion of memory, which we talked about just now. That memory is can be understood as long as you have some energy that caused some object to change its state. In some ways, it's very slippery, but, arguably there's a point there. You cannot deny that, there's just different scales of memory. One scale difference being on the dimension of time, okay? And of course, space, right? But so as long as you have where a relative permanence in the change of state as a result of some energy, you might think of that as memory, or at least I think of that pretty convincingly. But of course, this is still a debatable kind of philosophical question, right? What does it really mean? All right, so we'll talk more about content addressable and index in a bit, but apart from wanting to address, Hopfield wanted to address the issue of memory, but beyond just that, he wanted to address it in the sense that because he wanted to understand memory in biological systems, he noted, right, that biological systems operate, specifically the neurons, operate by what we call as Hebbian learning. And we will unpack that more later on as well. So in other words, in trying to understand or solve or implement memory in that models biological neural network systems, Hopfield noted two things. One is that this system, as according to our common experience, must be doing this memory in a content addressable manner. And second, it must be doing it in a Hebbian manner because of observations at that time. Okay? So these two must come in hand. So alternatively, you can also construe it as this. Does a system that does Hebbian learning therefore necessarily or like sufficiently instantiates content addressable memory? Okay? So like if I do Hebbian learning, does that allow me to have content addressable memory? Vice versa, I do content addressable memory, can I use Hebbian learning to do that, right? So in doing this model, is trying to kill two birds with one stone, to prove that. So the hypothesis here, a neural network that does Hebbian learning, spelled that wrong, Hebbian learning, does content addressable memory. That's the hypothesis, okay? So if I can implement a model, a neural network, and have it do Hebbian learning, then I see whether it does content addressable memory, and we will unpack what that means even more specifically, okay? So let's talk about the difference between content addressable memory and index memory, and to do that, let's talk about index memory. What is index memory? Essentially, we're talking about the best example is computers. By computers, we're not talking about the function of computing, things that compute, but specifically the desktops and iPhones, machines that we use, or devices that we humans use in our daily lives. Okay, they essentially do index memory. And what is index memory? Is that in these machines, in these hardwares, you get a chunk of gates, of logic gates, or magnetic volumes, okay, where you might store the data or the information that you want. And in order to, and so this would be in terms of, in binary, it would be strings of binary things, right? Now, I draw it like this as if it's one chunk. Obviously, we have it used to be like this, right? But, I don't know, anyone from computer science background? No? Ah, it's so cool, because now, our memory is stored it's so powerful. That's why we have information robustness and all that. It all comes from Shannon and information. Anyway, okay, so I can ramble on and on. The ones and zeros not necessarily stored together in one place. They can be spread out, right? There's many, many creative ways to store data for robustness, so that even if because last time if you drop this, that's it, right? Now you dropped it, it has some built-in robustness, and it's not just the physics, the physical thing, but in terms of how the information is encoded, it's really genius, okay? Worth knowing a little bit more about how they do it. But doesn't matter. The point is there is a set of space, okay, in the machine itself, where it's like the flip-flop gates are zeros and ones that represent some information that you wanted to encode. So for example, I have a notion of cat. I'm going to draw it on the right side here. Okay, and let's just say that let's make cat 0, 1, 1, 0, 0. That this string of 5 bits. Okay, it's a 5-bit word. We say it like this. This is a 5-bit word. This 5-bit word could represent different types of information or features. Okay, and we say that these features, represent what a cat is in the external world. All right, and maybe we put it here. So maybe this is cat here. All right, I said 0, 1, 1. Okay, let's make it very obvious. Oops. Okay, and then we say cat is here, located here. Okay, then we have another notion that a cat meows. Or this notion of concepts, or stimuli, a sound, all right, that audio recording, okay, and it is represented by the 5-bit word 01110, okay, and let's say it's located here in this part of the hard disk. Okay, now if I put cat here and meow here, and I want to retrieve the cat and the meow in index memory, what it will be is that I have some sort of a marker here, right? To say if you want me to retrieve cat, I convert it to some location, right? All the information to do with cat, the cat file, okay? Then I go to this location, which is for a lack of a better way of representing, let's just say that it's x and y coordinate, okay? So I go to x0 and y1 or something like that, okay? So that if you give me cat, okay, you put it into this computer, okay? Sorry, actually I should draw it like this. If you give me cat at the simile and you put me into do this compute, it will generate an x and a y, okay, like matching or something like that. And then it will go to this location, and then it will retrieve the cat file, will pull it out, okay? So for example, you type in the word, if you had a picture of cat, all the features of cat, and then you want to see all the features, you type in the file name, let's say cat.png, okay? Cat.png gives the computer some xy coordinate in its system. Go to this location. Then cat png file name, okay, means everything from here by how many more bits, 5 more bits, that's the information that you actually want, okay? Cat png is just the queue, the typing you did. When you type that, you want to pull out the picture, that's what it does. Goes to the number, goes to the location, and then shows you the picture itself, which is the actual file you want. Okay? So similarly, if I do meow, if I type meow dot, what's a MP3, right? Something, file, right? Search for it, gives me X, Y, and then goes here, and then plays the sound. Okay, right? That's how generally it operates. I mean, there's many obviously complicated things happening, but something like that. Okay, one question. Does it matter where cat, PNG, and meow, MP3 are located in the hard disk? So if this XY is, let's say, 10 and 20, and then this one is, let's say, 100 and 200, does it matter to the information itself? It's irrelevant, right? So it's very obvious, right? The relationship between the state the physical state, meaning the flip-flop gates, like where are these zeros, 1, 1, 0, 0, like this chunk, this 5-bit location, where it is, okay, the physical state of that location versus the content itself, information content itself, okay? This relationship which is the psychological bit, arguably, right? So this is the physical, which is the actual location of it, and the psychological bit, which is to us, it has meaning. That when I see the picture of a cat, I am the one having the meaning, right? If another machine sees the picture of the cat, there's nothing. As you say, no experience. We are the ones having the experience, okay? So the meaning, the experience, the psychological content part of it, and the physical state, right, where it is, the relationship between this is arbitrary. That's the key notion. Doesn't matter what the 0 and 1s are. Doesn't matter where these zeros and ones are located. Doesn't matter whether they are located in a continuous string or, as I said, fancy ways of encoding now, you can spread it out all over the place. you can transform it. You can say, I want to encode 01100, right? But then because of information security, I encrypt it. I put some 128-bit encryption, and then it becomes alpha, X, whatever, something else, right? So that if I want to decrypt it to go back, I have to do all this. You can do all these transformations and all that. It doesn't have anything to do with the actual experience or the psychology or the meaning of it. That is the key thing of indexed memory. And that's why computers are computers. And you might say that there's no experience. It doesn't care. Doesn't matter to its operation, to its memory operation. The experience is irrelevant. In fact, you don't want it to experience anything because it might say, I don't want to tell you this answer because I don't feel like it, or something is wrong, okay? Right? Okay, so that there is this notion of that there is this way of encoding memory, okay? It still involves changes in the physical states, right? Some energy changing the flip-flop gates. But the way this memory is done in an indexed way, in which the definition is that the physical state and the meaning of the content is arbitrary, it has arbitrary relation, then it seems qualitatively different from this, and it's not the way that Hopfield is saying that our biological systems work. Okay, it's important to appreciate this contrast because the argument is that we don't do it this way, we do it this way. So we don't do it the computer way. So you got to understand back then, they realized the phenomena is the computer has memory. Hopfield wants to instantiate memory like a biological system. The best example of memory we have that is visible is a computer. It has memory. But clearly, what this memory does, if we try to understand this memory, is different from our memory. Okay? So what is our memory? And as we said, it's content addressable. And what are the key features of content addressable memory? First is very, very clearly opposed from the index memory, where I said the physical state of that thing, the medium that is encoding the memory, and the information that is meaningful in that encoding, that relationship is arbitrary. So opposing to that is that for content addressable memory, if we change the neuron, let's just directly talk about the actual biological neuron that is used, that is, or involved, okay? That we change the neuron. If we use a different neuron, or we change that same neuron, but we change its state, so its level of activity, okay? That if we do this, is equivalent to we change the content. So it's in index memory, state and content are arbitrary. In diametrically opposed content addressable memory is exactly that the content is the state. So that if you change the state, you change the content. And if you change the content, it means changing the state. Okay? And by state, we mean the physical location of it, the physical state of it. Okay? Not just that. So in index memory, you can obviously change the file. You can, right? But what that is doing is just changing into a new information encode, right? But again, the state and the content is now a different content, right? It's arbitrary. It could be, you can change it back. Whereas here, you can't do that because the state and the content are bound together. So it will go back to, if we accept this definition, it will go back to the phenomena that, therefore, this system can learn things implicitly. And in fact, it actually, that's what it does. in essence. It's learning and encoding is an implicit thing. Even if we say explicit memory is based on implicit operations, right? Can you control your neurons exactly to tell it to grow or don't grow like this? You can't, right? It is just going to do its thing, and in its thing that it's doing, some of it is implicit, some of it we experience as explicit phenomena, but it's actually implicit operations still. Okay, just different levels, that's all. And we have a phenomena called false memory. In index memory, if it's an error and the computer crash, right? In our memory, okay, it's wrong, but I'm still alive, and I can still function. In fact, I can go back and say, oh, okay, I can very robustly change my memory without worrying things too much. Whereas a computer, if it crashes, it can't change its memory unless you tell it or implement some code, contingency to let it do that. And then it is fuzzy categories. It has fuzzy categories. So where index is like, it's either 0 or 1 in this location, and then the whole file is different if you change it, right? For our memory is if you change one thing, it doesn't change the whole thing. The whole thing still is more or less stable, okay? Except maybe some things is just a little different, but that's acceptable, all right? So these are the features that, so because it's fuzzy, this is tied on to the notion that it is analogical and not digital. Okay? I think no issues there, right? So these are the very, very key differences between content and index memories. And this is, now we are so used to computers, and computers are so complex. We don't think, oh, is this really that big of a deal, in terms of the differences? But back then, I mean, can you check the Hopfield paper is published what date? 80s? Yeah, 1980s, right? 80s. Okay. Having a computer in 1980s, no one has computer in 1980s. At least not at home very easily. Yes, they did have computers, right? But not like this. Certainly don't have this. Okay. And 1980s, we're still using the landline to call. You all know, right? The ring one. Have you seen? To dial the phone, you turn the ring instead of pressing or even talk. Okay? We have to memorize phone numbers because we cannot say the name of the person in the phone. So then they were thinking about things like that in 1980s. This is not trivial. Okay? All right, so that's the difference. And the challenge was to implement that content addressable memory. The second challenge, and this is where we need to introduce this fella here. Also, by right, Nobel level kind of thing, although I don't think he got a Nobel Prize. But in any case, he forwarded this notion, and Hopfield noted Donald Hebb's work, where it's through observing actual samples, okay, of neurons, I guess in vitro or something like that, or even in vivo maybe, I'm not sure. But he noted that neurons that fire together, very famous statement, wire together. And if you read the paper, and if you also go into Donald Hebb's work, you see what it means. It's a very, very specific observation that you get phenomena like NMDA receptors. Okay, these are real things that we observe, okay? And the synaptic functions, and it is activity dependent learning. That Hebbian learning is characterized by this principle that neurons that fire together wire together, and how that's implemented is in the fact that when you observe under microscope neurons, they have these things. I mean, you can do the necessary staining and all sorts of procedures. You identify that there are these things at least, right? There are many others, but at least there are NMDA receptors. They operate at synapses, so it's neurochemical, okay? And then it's activity dependent, that the receptors and their sensitivity at the synapse is a function of how much activity that its current activity is a function of its previous activities, okay? So, and it's operated by these biological biomolecules and these biomechanisms, all right? And through these substrates, we get phenomena like long-term potentiation, or LTP. You get short-term potentiation, STP. You get LTD, long-term depression. Okay. In other words, like if you make these, if these neurons have been firing together, then the next time this neuron fires, it is potentiating over the long term that this one will be likely to fire as well. It can be long term, can be short term. Vice versa. It can be that if I fire and then if I don't fire, right, then over a long time, I'm not going to respond to you either. And if I fire or you don't fire or we don't fire, then over a long time, we are not going to have strong relationships either. Works both ways, okay? So this is the phenomena that Hopfield was trying to integrate the psychological aspect and the neurobiological aspects. So this is the challenge, okay? We have to talk a lot about these concepts because the key here is really not about the modeling per se, but how do we approach modeling problems, neural network modeling problems? You will find that a lot of it is actually quite theoretical and conceptual. It's not so much of like, I want to do this coding and all that, right? But that they have done something quite profound in their work. So the challenge is to implement content addressable memory. Let's now move into something a bit more formal. So we've been talking about very fuzzy concepts, right? Well, not so fuzzy concepts, really challenging concepts, but these are like in the abstract domain. Let's make it more concrete. So kind of like our perceptron last week, where we translated the logic table problem from, if Socrates is human and all humans die, that's a very fuzzy abstract thing. We translated it to a logic table and then we implemented it in a perceptron with an architecture and an activation function. So let's do that now. We have the challenge, fuzzy challenge, content addressable memory. How do we translate that? Formally, we state it like this. Let S, okay, so bear with me now. It's going to get a bit more technical and mathematical. Be equals to this set of numbers from 1 to n that represent sets of distinct states. And where states are item features. No, let's make it redundant. States of item features that we wish to encode and retrieve. As you guys rightly described just now, okay? A key part of it seems to be that there must be some encoding done of information, okay, states, and retrieve, some retrieval done. Moreover, for Hopfield, okay, based on, and this is key, sorry, themselves. All right. And I'll note here the self is the notion of auto, myself. And why this part? Okay, why this part here? Is because this is the notion of content addressable. That you are your memory, as I said right from the beginning. That if you did not have memory, you are not you. And that you are you because of your memory. So if you want to implement content addressable memory, and we agree that we do content addressable memory, what we are meaning is that we want a system in which that if I had many states that I experience, so to speak, whatever that means, operationally, formally, that means that I want to encode, and with the hope of retrieving these states, right, in which the way I encode these states is that these states are those states themselves. All right? The features of it are themselves what drive the encoding, or are being encoded themselves. All right? So, so that's why we frame this as the formal expression of the problem. Okay? So we begin with this notion that there is this set of energies, environmental information out there represented by S, and that now if we extend it, so that if you if we instantiate this notion of S, then we can also say let N be equals to the length of S, all right, and that is the number of different states. Let's encapsulate this. Imagine your whole universe. The whole universe, there's only those 4 different states to encode, or 5 different states. Obviously, the universe has infinite number of states of things to encode. But let's reduce this formally to, okay, not make things so complicated. Let's imagine that for this system that we are going to make, its universe is this n number of states of whatever features there are in this universe. That there are only these n states. Okay, that's the length of S. All right, and so putting this together, what we want to do is we are in. Hence, that's why we say Hopfield network is an autoencoder. We want to auto-encode. All right, and also we want to do auto-based retrieval. Retrieval is always with respect to the self. Okay, so this is stating the formal logic first. We move on further. Any problems here? Okay, right? So let's move forward with a sort of data table. So imagine the universe is defined by this feature space. Okay, and that this feature space, let's imagine that the universe only has these 5 phenomena. That the universe either has leaves or no leaves, is made of wood or not made of wood, has fur or not furry, has a tail but not or no tail, and meows or doesn't meow. Okay, sounds very arbitrary, but let's just imagine that that's all in this weird universe. Okay, that's all you can have. These 5 dimensions, and these dimensions can either be ones or zeros, having this or not having this. All right. Then let S. Okay, and essentially, let's say S has only 4 possible states. Okay, in this universe, and let's say a cat is the first state that we experience, and this state will be defined as what? Does the cat have leaves? Nope. Is it made of wood? Nope. Does it have fur? Yes, yes, yes. So in this 5-bit word, in this 5-dimensional universe of binary universe, I have a state that I call cat. Let's make this even more concrete. Let's complete this data table. So as I'm doing this, I'm also demonstrating to you how to translate a real problem into an operational one, and that we can then solve in coding terms. And if we solve it in coding terms, it translates back to these real-life problems as well. You see the path of how the argument and the study is done, the simulation is done. Okay? And I had a hard time thinking about this one. But whatever, okay? It's a very specific universe. Because then I can do this. Okay. Although it's like, what? Why? All right. So, let's go back. I have S states, distinct states, okay, made of item features, right? And that I want to encode these states. So what do I have to encode? This 00110, these 4 different 5-bit words. I have to store or represent these 4 different 5-bit words. That's the encoding part. And I have to do it such that this encoding method is themselves those 5-bit words, 1. And then I have to retrieve as well, right? Based on those auto 5-bit words. So then, beyond just having this S, I'm going to also have such that given leaves, okay? That is, what is leaves? This is leaves, right? I will get a tree. Which is 1, 1, 0, 0, 0. Okay? And we call this the probe. And yeah. So that I can do it this way, like and we have to do this using the Hebbian for Hopfields. for Hopfield specifically, we want to do this using Hebbian learning because the hypothesis is that a network that does Hebbian learning can do content addressable memory. All right. So essentially, what we're doing is that if we have a function called, let's say, a Hebbian learning function, all right, that results in a Hebbian, let me write it in a more correct way. I have a neural network. It learned things by Hebbian, and I give it 1, 0, 0, 0, 0. It will give me 1, 1, 0, 0, 0. This is the formal statement of what we are trying to achieve. So this is roughly, this is the data table. So kind of like the logic gate that we dealt with. Okay, so, and then in doing this also, note, this instantiates decentralized or localization of representation. Right, so someone mentioned decentralized memory. Because it's decentralized because I don't need the whole thing to retrieve the whole thing. I just need one thing of it, and then somehow that can be used to retrieve everything from everywhere else. Okay? All right, any questions here? This is the formal jump, further formal jump. Okay, so that if we are talking about solving content addressable memory, that's equivalent to expressing it this way. We have a data table that looks like this, and we want to use this table to instantiate a function, okay, using some Hebbian, specifically a Hebbian one, where if we give this kind of probe, it will give us this kind of answer. Okay, all right. This is the formal expression, and we carry on, there's more. So that was the first step, okay, to establish the data table. Second, we remember we need an activation function. If we want to deal with a neural network, then we need an activation function. And for the intents and purposes of this work, when we want to model according to what Hopfield did, Hopfield was very practical. Sorry. If you read the paper, I would try as much as possible to stick to the paper, but sometimes I might use my own notation to be consistent across different papers, right? But essentially, you get the same idea. This is the binary regularized linear unit, and you will note the indices that I have AIK, meaning AI is the ith layer, which is the input layer, and K refers to the kth node that is in the input layer. And therefore, correspondingly, you have the weights that connect node AIK to node or unit AJ rth unit. Okay? So the output layer, J, the jth layer is the output layer, so to speak, and the jth layer can have R units as well in this case. In the perceptron, we always only have one AJ output, but actually your output can have more units as well. So here AJ is expanded to have R units, all right? So where these are the connecting weights, obviously. Okay, so this is a threshold function. It is a binary ReLU. We labor this too many times, and it's a binary regularized linear unit. We know this before, and it looks like this. And it's got a theta here, and this is going to be AIW, and this is going to be AJ. All right? And essentially, we will implement it. Oh, sorry. We will implement it when you write the code. You will be doing this one. Okay? All right. I don't think this is a problem. We've done this before, and this is the activation function that Hopfield uses. Okay? Next, and this we haven't done before, and this is the new thing now, is that we also need a learning rule, or the updating rule. Okay? And to update what? We update the weights, the W's. Okay? The activity or the pre-activation state and the activation states, there's no learning or updating to be done. They just respond, right? The node is just active or not active depending on the activation function. What is being learned, or what the learning does or updating does, is in the weights. All right, so you update the weights, or you learn the weights. Okay, so, and specifically, we want to learn it in a Hebbian, using the Hebbian learning rule. And this is where Hopfield is just a genius, because he declares that the learning rule is like that. Let W k's of I and r's of j be equals to, if you've read the paper, sum over all the states and in this here, we put the s here, is not the power of, it's what it means is the summation iteration of, okay? Just so you know. Just be careful here. The s doesn't mean like to the power of that. It just means that this is the s iteration because of the s summations, okay? So that k's of I, very weird, 2a minus 1 times 2a j's of r, r's of j, s minus 1. And then he says that this is the Hebbian learning rule, like that, okay? And moreover, when k's are equals to r, then the weights are 0. And this we call it equation 2. Okay? Declares it like this. All right? And let's hang on to that, like why the, I talked about it, right? If you implement this Hebbian rule, if you work it out, when AI and AJ are the same, W becomes plus 1. When AI and AJ are different, then it becomes 0. Yeah? And actually, when they are the same, includes 1, 1, and 0, 0. Right? Then they will also similarly activate. All right? So you can see the flavor of how it is. Things that fire together, wire together. If the states are the same, they will wire together in the sense that the weights will increase. Okay? And if they are not, then the weights will decrease or remain the same. All right. So let's visualize this a little bit more. Let's visualize this in operation. So let's put cat here, dog, tree, and cotton. Okay. such that S is comprised of elements. It's a 5-bit word, right? So it's AI1 to AI5. We can summarily say that this is a vector at state S. In fact, specifically, first state cat, right? Or let's just say, yeah, it's just to get you into the notation mode. Similarly, AI1 can change. And you might have, or a different state. So the inputs can change depending on where you are in this universe, what you encounter in this universe. The length, as we said before, is equals to 4. All right? We have to specify this so that the modeling makes sense. When you describe the model, and if you read my sample paper, right, we do some, when in writing modeling papers, you do have to write some technical stuff as well. All right? And then we call that, these are the input nodes. We talk about K, has 1, 2, 3. K comprises of the numbers 1 to 5, and these are the input nodes. R also comprises of numbers 1, 2, 3, 4, 5 specifically, but we call these the output nodes. However, in this Hopfield implementation, this is where you have to do a switch. In the perceptron, you are used to input, and then something gives you the output, separate, like a forward in time and space, that kind of thing. However, here, and you will see this in a minute, in the Hopfield implementation, input and output refers to prior and posterior. Of A star, which are nodes of activity, or activity of nodes, rather, node activity. A star node activity, yes, okay. All right, so what it means is that instead of thinking about AJ as kind of like receiving input from separate AIs, what it is that this node, this neuron, right now is AI, and later it will change its state, right? And that's its AJ instance, okay? Let's make this a bit more concrete here. We want to auto-encode. I have I space. This will make it even clearer. The mission is to do auto-encoding. This implies that we want to make the posterior state equals to the prior state. Okay? So I have this network. Initially, they are at AI state. I want to make, they will then become AJ state. But specifically, I want the AJ state to be equals to AI state. That is the notion of autoencode. It's really weird. You have to think about it a little bit, right? But that's essentially what they're trying to do. Now we specify that AJ is equals to the A's of I in the vector notation, okay? All right? Specifically, if I were to do AJR is equals to sum of K, AI, K, J, all right? Where K is not equals to R. All right? And this was equation 3. Okay. How do I draw this out? So initially, I have AI1. This is now the architecture, right? So I'm going to put a note here. So we have AI1, and then it looks like this. This will become AJ1 later on. Okay? So that AJ1 is equals to the WI2 J1 weight times AI2, WI3 times AJ1 weight, okay? WI4 times AJ1 weight, WI5 AJ1 weight, sorry, WI5 J1 weight times AJ5 activity. Okay, so AJ1 is going to take these 4 inputs, but this weight is equals to 0. That's what this equation 3 means. Does that make sense? This is how you visualize it. Yeah? Okay, any questions? So that if you put it all together, let's switch bases here, okay? So I'm going to now, how should I draw this? Let me redraw this here. Okay, so we have the AI, 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 WIJ, J. This one is equals to 0, right? So we say that this AJI is equals to the sum of all this K, AI, K, WI, K, J. All right? In this instance, it's like that. But later on, we're going to switch. If we take another basis, it'll be something like that. So same 5, 1. But then we're talking about AJ2 now. So this will be AI2, AI1. Sorry, the writing is horrible. Okay, but in this case, the W's have shifted. So then if you keep on playing the game, it'll be AJ3. And AJ3, it'll be okay. Let's not forget, of course, and similarly, okay, so can you imagine, all right, if you rotate it, every time you're talking about a different AJ rth unit, you are receiving stimuli or pre-activation input from different sets of your neighbors. Essentially then, for a 5-bit universe, the Hopfield network looks like this, right? You can, am I missing it? Yeah. All right. This is the I, the J is outside, and that's the Hopfield network. Okay? Is this visualization okay? That's what it looks like as in terms of visual architecture and how the weights connect to each other. Okay? I do emphasize that this obviously is all as concretely as we draw it out. It won't become clear until you code it. And then when you code it, then it becomes even clearer. So we do this one layer at a time. Okay? All right. So, yeah, just 2 more things, and then I think we will have enough for today. So if we have this representation, this one, okay, 5-bit word, and they are connected to each other. Initially, is the I state is the inside, and then after update, after you learn, you change the weights, but then the result is you change the weights in a way that the IJ becomes like the AJ becomes like the AI, okay? So this is the visualization of it, but in terms of coding, really, you need to also think of it in terms of an array, okay, the actual array, so that if you have AI1, AI2, AI3, AI4, AI5, you also have correspondingly AJ1, AJ2, AJ3, AJ4, and AJ5. Okay? And so this will be the I state, this will be the J state, and this will be the W IJ array. That is the key thing that we want to learn, right? We want to update the weights by 2AI minus 1, 2AJ minus 1. Okay? This Hebbian function, this Hebbian learning rule, is going to drive the W, the big W array. And remember, one thing was very easy was that, so each of these would be the W I1, J1, right? And this is W I5, J5. Okay? And this is W I1, J5. And this is W I5, J1. Okay? No problem, right? All this array, this is the positions. But the key thing to appreciate is that actually zero, 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 0, 0, right? Because when k equals r, the weights between them is 0, which is this one here. Okay? And then anything else would be the equation, so that the W's will be updated according to some function of 2ai minus 1, 2aj minus 1. All right? And in fact, all these tiny values in each of these arrays, okay, the change in weights at least, okay, is each of these functions. And so which summarizes this is ai vector, this is aj vector, and then you have the w vector and the change of w's, just emphasizing that all the stuff in yellow, okay? I realize it's very confusing, so I don't want the yellow. Okay. Okay, so when we implement the code eventually, not today, we will be working with this kind of array where we have input states a's of i's and the output states a's of j's. A's of j's are the posteriors of the a's of i's, and their relationship is a function of having this W array, and the values in each position of the W array is the Hebbian learning rule that will be incorporated into that. It's not so clear how this really fits, but these are the components of when you actually code it. We will be working with this array and how this array changes. And you can see that this array changes as a function of the AI and the AJ, right? As this table shows, okay? And specifically, if it changes according to AI and AJ, according to the 2a minus 1, 2a minus 1 thing, then it is changing in a Hebbian way. And we will see if doing that, how the network performs. We will then test it and evaluate it, all right? So, any questions about this? Again, it will become even clearer when we do the coding, but I just want to introduce, this is how to think about it. We just jumped from a very abstract conceptual problem to a more formal data table. We talked about the activation function, which is the binary ReLU. We talked about the learning rule, which is the Hebbian rule. And we talked about the architecture, which is the 5 pentagram thing for a 5-bit word. Obviously, if you have a n-bit word, it will be a bigger circle, right, with more connections. And W will be bigger, okay? All right. Okay, so last thing for today is, of course, oh, why is it still there? We have to ask the question, why equation 2? And if you remember equation 2, 2ai minus 1, 2aj minus 1. And this giving us, we use this to calculate the change in weights, and that why we call this Hebbian. Okay? I mean, I think we worked it out before. It's pretty simple. If you look at this, when AI is 1, AJ is 1. So remember, our world is binary. So there's only 4 possible states. Yeah, we worked this out before. When it's the same, the weights are increased by 1 unit. When they are different, the weights are in fact decreased by 1 unit. And when they are the same, but both are same in being inactive, both, they're still the same. So, this is actually the XOR, isn't it? It's the XOR instantiation. So that is when A states IK, and remember when I put S there, I mean across all the possible states, and in this universe we have 4 possible states: cat, dog, tree, cotton. Okay? So when an input state, when that node, K node, is responding to seeing a cat, a dog, a tree, or a cotton, okay? And its posterior state is like 0 or 1, whatever, depending on how it responds to that. Then the posterior state is going to be the same, all right? So if this neuron's right now response is similar across all states, across a particular state that it likes, this neuron likes, let's say this neuron likes cat, okay? Then its response to cat, new cat, is going to be, to make its response to new cat, the new probe of cat, to be the same as its past response to, cat that it encoded. This, whatever its initial, whatever its initial weight, give myself a bit more space here. Add 1 to it, okay? Whenever the state is the same, add 1 to it. Otherwise, make it -1. So when we implement this learning rule, you will see it's a very simple one-liner. If it is the same, +1. If it's not the same, -1. In fact, that's what this Habian rule is doing. Okay. So in doing that, we will see that when we implement this model and you evaluate it and test it out, that it will have the phenomena of all we said, content addressable memory. And we'll also be talking about how to evaluate that, how to test that out. All right. It will become a lot clearer as we implement it. Okay, so for today, I'm going to stop here. Next week is a holiday, right? So we won't have class. So please finish your homework too, okay? And do read up on the Hopfield network if you haven't. Try to read the paper. A fair warning, it's not easy to read, okay? But I hope that when I give you these clues and bases, that when you read it, it might make a little bit more sense, okay? Maybe it won't make sense at all, but it doesn't matter. Try, okay? And next time when we come 2 weeks later, I will do a bit further more of the theory. I will show you, we will prove how and actually it's in the Hopfield paper. That's why I asked you can try reading, because he proves using these learning functions, activation functions, and the architecture, that implementing this implements content addressable memory. Mathematically, he proves it, all right? But he proves it doesn't mean that it's analytical solution. It still means you have to run the simulation in order to validate it, okay? So what the proof will show is that there is a case that when you do things this way, there is a trend, all right, towards content addressable, what we might call content addressable memory. But still, you will need to run it in order to validate that that's what it's doing, okay? All right, so up to this point, I'm going to stop here because there's enough detail for today. So fair warning, do read up Hopfield's paper, because the next lecture will be even worse for the mathematics part. He deals with that in the paper, so it will be helpful to understand the paper a bit better before we talk about the proof in class. The proof is not important though. What's important is the implementation. But I do want to go through the proof with you guys so that you get a picture of why this is a very, very solid piece of work. And but beyond that, from this mathematics, we will be applying it. That's the more important thing. Can we apply it? Can we actually, based on Hopfield's paper, recreate the Hopfield network based on these principles and these formulas? Okay? All right, any questions? It's a lot, I know. But it's very fundamental, very broad topic. And really, if you can do it, you can feel proud of yourself. You have something to be proud of. That's it. Okay. And I emphasize one more time. We are going to do it not by using any TensorFlow or PyTorch. We're just going to use basic mathematics, right? Yeah. Okay. Any questions? Okay, if not, then I'll leave you to it and have a good long weekend next week. Enjoy yourself, relax, enjoy reading the paper as well, I hope. We'll see you in 2 weeks' time. Don't forget to hand out your homework 1 by tonight, midnight. And then don't forget, because I won't be around to remind you, don't forget to hand out homework 2 next Friday as well. Okay? All right, so that's it. Thank you.